Welcome back, everyone. So thanks for those of you who are here for coming despite the slushy snow. So I hope you enjoyed Tuesday's lecture. I sure did. But you're back to being stuck with me, for better or worse. And so before we dive into today's material, I've just realized that I haven't written down my sentence. So, oh no, I have. Okay. So before we dive into today's material, I'd like to give you the Italian expression. So I like that Prakash was able to give you something of an Italian flavor. I'll give you an expression, as usual. So today's Italian expression will be the following. It's la solita minestra, which means the usual soup. Hello. The usual soup. The usual soup. But it's really used to mean something like the sort of usual routine or the usual story. So the usual routine. But for some reason, well, no, actually Italians love soup. I love soup. And so that's why it's in this expression. So what's a sentence that's more or less relevant to you in which I use this expression? This is my sentence. Cesare hopes that after Prakash's lecture, the 330 students aren't too sad to get back to la solita minestra. So I guess in this case, I'm the soup. I don't know. Okay, so I don't have any serious announcements to make. Hello. And so we will jump right into the material for today's lecture, which is very exciting because it is about everyone's favorite topic, reductions. So today we will be showing that a problem is undecidable via what's called reductions, and in particular mapping reductions. So they're not the same type of reductions as the ones you see in 360. They're much easier. Before we do that, I'd like to quickly sort of review some of the stuff that Prakash talked about, because Prakash really just gave you the intro of undecidability, which is really common in these types of theory of CS classes, where you just talk about the halting problem as the first problem, which is undecidable, and then you work from there to show that a lot of other problems are undecidable. So the main idea that we're going to be doing for the next few lectures is we're going to take this sort of canonical undecidable problem, the halting problem, and then we're going to show that many other problems are also undecidable. Okay, so we're going to sort of build a toolkit of undecidable problems. But before we do that, I'd just like to recall this distinction between a language and a decision problem, because sort of Prakash implicitly shifted the discussion from languages to problems without really announcing what was going on. I think I'd just like to make things slightly more explicit. So what is this connection between languages, which we've been studying, for 18 lectures, and decision problems, which is now going to be the focus for the rest of the semester. Okay, so this is a quick reminder definition. This should be relatively familiar for you. But a decision problem, which I'll abbreviate as DP, is a problem where given an instance, so this is a term that I'm going to use a lot starting today, right? An instance of a problem that's just, you have some problem and you instantiate it, and that's that particular instance of that problem, right? So we'll see a few examples of that in a second. So an instance of that problem, the answer is either yes or no. Is either yes or no. Okay? That's a decision problem. It's called decision problem because there's a decision to be made, which is given this instance, yes or no, right? And so what's an example? This is an example that I'd even given at the start of the semester, I think during lecture 2. And so this is the prime of n decision problem. So what does the prime of n decision problem say? It says, given some natural number n, is n a prime number, right? This is the prime decision problem. And so what's an instance of this problem? An instance of this problem is, for instance, if I give you n is equal to 7, and then an answer to this instance of that problem is yes, right? So we have a problem, we have an instance, and we have an answer. Okay. Another problem, which Prakash discussed on Tuesday, is the halting problem. So the halting problem, which I will abbreviate HP, but I think Prakash used HTM, but it's essentially the same thing. So HP is parameterized by two elements. The first is some Turing machine M, and the second is some input string X. And in the halting problem, the question we ask is, given a Turing machine M, and an input string X, does M halt on X? Does M halt on X? Okay. And so you might be thinking, well, this is quite different from Tuesday's lecture. We were talking about programs, but like Prakash said, Turing machines are the most powerful models of computation, so whatever else you talk about in terms of formalism is equivalent, right? So if you talk about programs, or if you talk about the lambda calculus, it doesn't really matter however way you ask this question, it's still, in essence, the same decision problem, okay? And so, in this case, what is an instance of the halting problem? Well, an instance of the halting problem is, you're given some Turing machine M, or you can imagine you're given some program in, your favorite programming language. It looks like something like this. It has some accept state, and it has some reject state. And you have some input string X, right? So you have, 0, 1, 1, 0, 1, supposing that sigma is 0, 1. Okay? So this is an instance, right? This is an instance. And perhaps, in this case, the answer is no. Right? So perhaps the answer is no. Because maybe, I don't know, somewhere here there's a loop. And given X, 0, 1, 1, 0, 1, the machine loops forever here. Okay? So then, in that case, the answer would be no. So that's an instance of the halting problem. Okay, so now what's the connection between a problem and a language, right? So I'm trying to get things back to formal language theory. Well, here's a definition which makes this connection. So supposing we have some non-empty alphabet, and usually we will assume that sigma is 0, 1. You'll see why in a second, but the intuition is, you could take any program in any programming language and convert it to machine code. Machine code is just a sequence of bits, right? So zeros or ones. So I'll use this terminology. The language of a decision problem, or really corresponding to a decision problem, which I'll denote L sub dp, is the language containing all instances of this decision problem dp, where the answer is yes, and the instances are encoded as strings over the alphabet sigma. Okay. So I'm reusing much of the terminology that I've just introduced. I have instances, decision problem, and answer. But now I'm also introducing a new term, which is encoded. Okay. So encoded, Prakash talked about that during Tuesday's class, but I'll review it right now. So what are a few examples of languages that correspond to decision problems? The first one, let's say if this was example, okay, good. So this first one corresponds to the example 1 of the decision problem that I gave. So it's L sub prime, right? L sub prime. And so the idea is you take all of the yes answers to the prime decision problem, you encode them some way as strings, and you place them in the language. Well, what's one way of doing that? Let's just use the length of the string to represent the yes instance, right? So let's just take 0n, 0 power n, and let's just say all the strings in L sub prime are strings only with zeros, but where the length is prime. Okay, and so then the idea is, L sub prime contains some string x, if and only if x encodes a prime number, n using the alphabet 01. 01. Okay. So in other words, it's encoding a yes instance, right? So how can we do this for the halting problem? So to do this for the halting problem, I'm going to use the notation that Prakash introduced. Supposing that I have the alphabet being 01, then the language corresponding to the halting problem, L sub HP, is the encoding of instances of the halting problem where the answer is yes. So the way we're going to represent that is we're going to take a Turing machine M and some input string X, and then we're going to describe this as a string. So to do that, the notation is going to be left angle bracket, right angle bracket. Okay, so you can think of this as the binary representation of M and X. Okay, so I mean X is very easy to represent in binary because it's already a string over the alphabet 01. M may be slightly trickier, but we know we can do this because we know that we can convert any sort of programming language into machine code, which is just a sequence of 0s. So it shouldn't be too surprising that we can do this for a Turing machine. So for instance, we could say if we have 10 states, then let's use 10 zeros to represent each of the states and do something like that. Okay, so I won't give you details on how to encode it explicitly, but if you're interested, you can come talk to me after. Okay, and so we take these binary representations of Turing machines and input string X, but we only place them in L sub HP if, of course, M is a Turing machine, X is in sigma star, and the most important condition, M halts on X. Okay, and this is L sub HP. Okay, so this is the language corresponding to the halting problem. Okay, and so the idea is on Tuesday, Prakash showed you that the halting problem, the problem of determining whether, given a Turing machine and some input string X, does the Turing machine M halt or does some program halt? This problem is undecidable because there isn't a decision procedure to decide it, right? We get sort of logical fallacies whichever way we look. And so the idea is you can relate an undecidable problem to an undecidable language. And the reason why we're talking about languages is because they help in explicitly or formally writing down what a mapping reduction is, which we'll do in a second. Okay, and so let me just say that in this following definition. A decision problem is decidable if, and really this is an if and only if because it's a definition, its corresponding language is decidable. Okay, and so the language corresponding to the halting problem is undecidable because the halting problem itself is undecidable. There isn't a decision procedure which decides it. Okay, so this is more just of a review of Tuesday's lecture. Okay. Okay. Any questions about this? Should be clear. No? Okay, good. Okay. So with this in mind, with the fact that we have decision problems, we have their corresponding languages, and we can have languages which are both decidable, which are either decidable or undecidable, what we're now interested in doing, and what we'll be interested in doing for the next few lectures, is showing undecidability. So we want to show undecidability. Now the question you might ask, and rightfully so, is, who cares? Who cares about showing undecidability? Okay, so this seems very theoretical, very abstract. Why would we care if some problem and its corresponding language is undecidable? Well, there's a few reasons. So if you can show that a problem is decidable, then you can say, okay, well now at this point I can start talking about its time complexity, right? And that's why you're taking 360. So you can see how efficient can I actually decide this problem. If it's undecidable, then you can say already, well, I don't really care about deciding it exactly. I need to stick to heuristics, and I need to develop heuristics which sort of cover most cases. And the nice thing about that is that no matter how sophisticated your heuristic is, there will always be a way to improve it. And so that's nice. That means that we all get to keep our jobs. So that's nice. So who cares? Us, because we get to work. Okay. So there's a few ways of showing undecidability. The first one is what Prakash did. So the first one is what Prakash did. He essentially assumed that the problem was decidable. So he assumed decidability. And he showed that this would lead to some logical inconsistency. And really what he was doing, so it might not have been clear to some of you, but really he was using what's formally known as a diagonalization argument, which he briefly talked about. So if you don't remember this from Math 240, hopefully you've seen diagonalization arguments. If not, that'll make me very sad. But in diagonalization arguments, you want to show, for instance, that the set of real numbers is uncountably infinite. And so the way you do that is you suppose that it's countably infinite, and so you have an index to every real number, and you show that you can create a new real number based on that index, which was never actually in that sort of list of real numbers. And so the idea that Prakash was giving was actually quite similar. It's sort of a bit hard to see it through the way he was explaining it, but essentially he was giving a new Turing machine that wasn't indexed by that list, because we're assuming really implicitly that Turing machines can be sort of indexed in a countably infinite manner. Okay. If you want more details about that, I'm happy to discuss it offline, but that would probably take 30 minutes to show formally, so I'm not going to do that. Okay. So that's one way of doing it, but that's rather cumbersome. And so the other way to do this, is through what's known as a reduction. Okay. So now we get to talk about reductions, which makes me happy because I like reductions. Okay. So before I get into how to use reductions for showing undecidability, I'd just like to review what a reduction is, because I know many of you already know what a reduction is. Some of you might not, or some of you might have forgotten, sadly. And so let me just refresh your memory. So what is the idea, the general idea of a reduction? So in a reduction, you're given two problems, P and Q. And a reduction from P, or of P to Q, so there's a direction to the reduction, is a method to show that some problem Q is at least as difficult as P. Okay? So this is what a reduction is. At its core, no more, no less, this is what it does. It shows you that if you have a reduction from P to Q, then Q is at least as difficult as P. And so it's a bit hard to see why you would say P reduces to Q. The reduction term doesn't really give you that intuition. The intuition that you get from sort of at least as difficult is from the actual notation. So we say P is, less than or equal to Q, but really we mean at most as difficult as Q. Okay? And we're going to use mapping reduction, so what we're going to do is we're going to denote this with a subscript M. So, you might be thinking, what does it mean to be as difficult as a problem? For instance, in terms of time complexity, right? So it takes you as much time, if not more, or it takes you as much memory, if not more, right? As many resources, if not more. So that's what we mean by a reduction, and we can use a reduction to show undecidability. We'll see that in a second. Okay, so how can we show, now the question is, how can we show that problem Q is at least as difficult as some problem P? Right, so how do we do this? Okay, well, the intuition and the really crux behind reductions is you want to show that if you could solve P, if you could solve Q, you could also solve P. to me, that's quite an intuitive idea, right? If I have two problems, and if I know that I can solve Q, I can solve P, then to me it does sound like Q should be at least as hard as P. Right. And so how are we going to do this? The general idea of how we're going to do this is we're first going to take an instance. So to do this, we're going to take an instance of P, some arbitrary instance of P, which I'll denote I sub P. I'm going to use its notation throughout the semester now. And we're going to modify it to look like an instance of Q. Q, which I'll call I sub Q. Okay, so that's the first general thing you do in a reduction. The second thing you do is you want to show that if the answer to I sub Q is yes, then the answer, in this case we're talking about decision problems, so that's why I'm saying is yes. Then the answer to I sub P is yes, and vice versa. Okay, so this is a bit abstract. Okay. So why, it's not really immediately clear why doing these two steps would help you show that, you know, if you could solve Q, then you could solve P. Well, to illustrate this a bit better, let me use a diagram. So suppose I started with an instance of the problem P, right? So I started with I sub P. Then I gave this to some magical computable function, which I'll call the instance modifier. And the instance modifier looks at I sub P, and it does some magic, and it returns I sub Q. So it returns I sub Q. Okay. And now suppose I had a Q solver, right? Suppose I had some algorithm which solved Q, right? Suppose I had some Q solver. Okay, so this first step here is really referring to step 1. And now this second step is really going to be referring to step 2. Right? So suppose for a second that I could solve Q, right? I had some algorithm, some procedure that solved Q, right? That gave me the correct answer given any instance of the problem. So if the Q solver then gave me the answer yes, right? Then because of this point here, then that means that the answer to the initial instance of the problem P would also be yes, right? So then I can say that if my Q solver gives me yes, then the answer to the initial instance I sub P is also yes. Right? If instead I have that the Q solver tells me no, then again, because I have this condition, because I have this second condition, then I know that the answer to the initial instance problem of P will also be no. Okay. And so now this tells me that if I can solve Q, then I can also solve P. And so Q must be at least as difficult as P. Okay. So again, this seems rather abstract. Let's make things slightly more concrete with an example. I'm not going to give an undecidability example quite yet. Let me give you a more general example. Okay, so hopefully this piques your attention. So for the final exam of Comp 999, some magical class in the School of Computer Science, there are 10 question types. There are 10 question types. So there's questions of type Q1, questions of type Q2, all the way to questions of type Q10. And there's two versions. There's two versions to the final exam of Comp 999. Two versions of the final. So the first version, exam 1, contains questions of type 1 to 5. Right? So it contains one question of type 1, one question of type 2, all the way to one question of type 5. Okay. So that's exam 1. Okay. Pretty easy, right? 5 questions on the final exam. Yours will be slightly longer. And then there's exam 2. So exam 2 contains questions of types 1 to 5, and exactly 1 of each. And then it also has questions of type 6 to 10. Yeah, that's a bit too long for a final exam. So it might not be 10 questions long. And now the goal is to show that exam 1 is at most as difficult as exam 2. And to me, this is intuitive, right? You have 10 questions in exam 2 and 5 questions in exam 1. Well, clearly exam 2 is harder, right? At least it's hard, right? Because maybe questions 6 to 10 are, freebies. Okay, good. So this is the goal. And now what I'm going to do is I'm going to use sort of these two ideas to show this. Okay, so I'm first going to take an instance of an exam 1 and then modify it to give me an instance of exam 2. Okay, so let's take some instance of exam 1. So exam 1. Okay, and let's feed it into the instance modifier. So the restriction here is that the instance modifier actually has to be computable, right? You can't just do some black magic. You have to actually give a procedure to the instance modifier for it to change an instance of exam 1 to an instance of exam 2. And so how's it going to do that? Any ideas? Louis? Yeah. You have, yeah, exactly, very good. You have an instance of exam 1, it has 5 questions. Just add the other questions, right? Very good. So add 1 question of type Q6 all the way to 1 question of type Q10 to the input instance. Very good. Okay, and so this was my input. My input was an instance of exam 1. And now my output is now an instance of exam 2. Excellent. Right? So now suppose now that I could solve exam 2, right? So I had some solver for exam 2, solver 2. Then solver 2 takes an instance of exam 2 and it produces the correct answers, right? So it produces the correct answers. So it gives me answers 1 to 5 and then to 10. Okay? And so now remember, the goal was to solve exam 1. And so to do that, I can just say, well, take answers 6 to 10 and just drop them. So just drop A6 to A10. And now this answer here, A1 to A5, is the answer to the initial instance problem, right? Yeah? So now clearly this shows that if I could solve exam 2, then I could easily solve exam 1. Right? And this is exactly what we'll be doing in reductions, with a few small caveats. So now remember what we're actually trying to show is we're trying to show that something is undecidable. So at this point, we've only done a reduction. So students get confused because they say, a reduction immediately tells me that a problem is undecidable. That's not true. The only thing a reduction does is it does this, right? It shows me that, say, exam 1 is at least as difficult as, exam 2 is at least as difficult as exam 1. That's all reduction does, right? It shows difficulty of problems relative to others. Now, where undecidability comes in, so, what's the point of this example? Is now, suppose we knew, right? Suppose we knew exam 1 was unsolvable. So, maybe questions of type 4 are just impossible to solve because the professor is very mean. I'm not going to be mean like that. Okay, so, well, if exam 1 we know is unsolvable, then it must be that exam 2 is also unsolvable, right? Then exam 2 must be unsolvable as well. Why? Because otherwise, right, if exam 2 was solvable, then we could go through this cumbersome process and actually solve exam 1. Okay? So otherwise, right, otherwise, we could solve exam 1. Okay. And so the idea that we're going to sort of see now is we're going to start with a known undecidable problem. So the only one we've seen is the halting problem. So we're going to start with the halting problem, and we're going to take the halting problem and reduce it to other problems. So we're going to show that these other problems are at least as difficult as the halting problem. If that's true, then that means that those other problems must be undecidable. Okay. And so this is exactly what we'll be doing. This is exactly the process in a mapping reduction. With a few additional constraints. So with a few constraints. So the first constraint, and I think it's the most natural constraint, is that the instance modifier must be computable. So there must be an algorithm which computes what the instance modifier is doing. So now you might be thinking that's a bit weird, right? We're talking about an instance modifier being computable. Prakash introduced something as being computable only for functions. But really, an instance modifier is a function. Okay? Why is it a function? Well, the instance of exam 1 can be encoded as a string, and the instance of exam 2 can be encoded as a string. So really what the instance modifier is doing is it's taking the string, which is encoding an instance of exam 1, and mapping it to a string of an instance of exam 2. So the instance modifier really, behind the scenes, is a function that takes a string and maps it to another string. And so that's why this concept of computable is well defined here. So that's the first thing. The second thing is the reduction has to follow a few sort of more strict rules. So the first one is that no post-processing will be allowed. So in other words, here in this case, this wasn't for a decision problem, but I couldn't do any post-processing after this solver 2 here. So I couldn't do something like flip the answer because it's a decision problem. So no post-processing is allowed, and you can only use the solver once. Because otherwise you start to get into the space of Turing reductions, which hopefully we'll get to time to talk about, but that might just be at the end of the semester. Okay. So that was the soft intro to reductions. Louis, yes? Yeah, so it'll be clear when we look at the formal definition of mapping reductions. Yeah. Because at this point, I agree it's not clear. You'll see. Yeah? Yeah, that would not have been allowed. But we're not really going to do any dropping because it's going to be decision problems, right? So the only real post-processing that you could do is flip the answer. Because the solver is either going to say yes, no. So really the main post-processing that you could do is flip an answer. You can maybe do some other stuff after, but yeah. Good? Okay, good. So now we're going to actually look at a more concrete example. We're actually going to show that a proper decision problem, so this wasn't really a proper decision problem, well, it wasn't a decision problem at all, is undecidable. So let's call this example A. So what we want to do in this example is we want to show that the acceptance problem, also sometimes called the membership problem, A sub AP, is undecidable. And to do this, we want to show that the halting problem reduces to, in a mapping reduction manner, the acceptance problem. Okay. So I'm using problems as the terminology, but really when we're going to define this formally, we're going to talk about the language corresponding to HP and the language corresponding to AP. But you just have to be aware that these two things are sort of, there's a one-to-one correspondence between them. So it doesn't really matter if we're talking about problems or languages as long as we're consistent. Okay, so the first thing you might be asking, well, is what is AP? So what is AP? So the acceptance problem also takes two parameters, and it asks a question very similar to the halting problem. It asks, given a Turing machine M, does M accept W? So in this case, not only do we want to know whether the Turing machine halts on the string, we want to know whether it accepts the string. So intuitively, that sounds like it's slightly, but not much more harder than the halting problem. And we'll see that come through in the actual reduction. Okay, so how are we going to do this? How are we going to do this? Let's see how here. So we're going to do a mapping reduction from the halting problem to the acceptance problem. Okay. So the two things I need to do is I need to first convert an instance, an arbitrary instance of the halting problem to some particular instance of the acceptance problem. Okay, so that's the first thing I'm going to need to do. And the second thing I'm going to need to do is I'm going to need to show that the answer to the instance of the halting problem is yes, if and only if the answer, so the answer to the instance of the acceptance problem is also yes. If I can show this, then I have the diagram that I showed before. I have this idea that solving AP would be enough to solve HP. Okay. So how am I going to do this? Well, let's start with step 1. So in step 1, right, suppose we're given an instance of the halting problem. So we're given some instance of the halting problem. Well, what does an instance of the halting problem look like in terms of binary encoding, in terms of a string encoding? It looks like mx, right? And what we need to do is, from mx, we need to create an instance of the acceptance problem. So what we need to do is we need to create an instance of the acceptance problem. And in this case, the types of the input to the instance of the acceptance problem are going to be the same. They're going to be a Turing machine and a string, but let's just call them something different. So let's just say n and y for now. Okay. And so the idea is I need to create an instance of the acceptance problem as a function, right? So really as a function of the instance of the halting problem. Okay. So this is really the crux of any reduction, is doing this step. Okay. And so at this point, this is difficult, because if you're just given this this instruction without knowing anything else, you could just spend a whole day just doing whatever, right? So what you need to do is you need to think about the actual goal of this reduction. So the goal of this reduction is you want to show that when the answer to the instance of the halting problem is yes, the answer to the instance of the acceptance problem is also yes, right? You need to show this, right? And you can make the reduction such that you can make the instance modifiers such that this is true. That's the idea that you want to do. So the first thing, right, is if you want m to, so really what you want m to halt on x if and only if n accepts y. Right? This is what you want. Well, there's already kind of a hint here, right? when you're doing the reduction is that it's probably not ideal if you know nothing about the input string. Right? It's probably much simpler if you just say, well, just set the input string to x. Because you know if m halts on x, you know the behavior of m on x, right? So if you set y to be x, then that already sort of simplifies the process. So maybe that's not clear. It'll be clearer after. But it'll be much simpler in this case if I just set y to be x. Okay. So that's the first thing, right? That's the first thing. Now I've sort of reduced, no pun intended, my problem to m halts on x if and only if n accepts x. Okay. So this is a bit easier. Why is this a bit easier? Because now, suppose I have some Turing machine, right? Suppose I have some Turing machine. So m is my Turing machine. This is m. And you know m has a bunch of transitions. If m was a program, if m corresponded to a program, it would have a bunch of lines of code. And then at some point, it would have an accept state, and at some point, it would have a reject state. So the idea that I want to embed in my instance modifier is, should m halt on x, then this larger Turing machine n, right, should accept x. So n is, of course, going to be built as a function of m. Right? Otherwise, you know nothing about n. So n is going to sort of be built from the Turing machine m. So this could be n. And now what do you want? You want m to halt if and only if n accepts. Well then, if m halts, right, if m halts, you know from our discussion of Turing machines that it either ends in the accept or the reject state. Right? Well, if it ends in either the accept or the reject state in n, just say, okay, take from the accept or the reject state a transition that goes to a new accept state. Right? So make a new accept state QA, and this is the accept state of n. Right? And so make a transition that goes from QA to QR, QA to QA, and QR to QA. And these transitions, right, they would be for all of the input tape, right? So, you know, because at some point your Turing machine is going to just get to the accept state, and it's going to have on its pointer some tape symbol. Well, for any of the tape symbols, just say that you transition to QA and n. And so now it does look like I have this behavior that I wanted, right? So if m halts on x, right? If m halts on x, then m is going to input x, and then at some point it's going to arrive maybe here. And then at that point, n is going to say, well, I see that you've arrived at the reject state. Let me go to the accept state and accept. If instead m does not halt on x, right? M does not halt on x, that means that it's looping on x, right? So, you know, maybe m is stuck in this infinite loop here. But then, of course, so will n be, right? N will also be stuck in an infinite loop, and so n will not accept x, right? Good. So that's the crux of the Turing reduction, of the mapping reduction. So this was step 1. And you know what? Let's just rewrite. So let's just rewrite step 1 without all this fussy transition diagram stuff. Because in your assignments and in the final exam, you don't actually have to draw out the Turing machines. That's just silly. Really, you can just write the procedure, right? So what is the procedure of n, right? So the procedure of n would be n on some input string, and I don't want to get these backwards here. Okay. So n on some input string w, right? So n is a Turing machine which takes some input string. Then what n will do is it will simulate m on w, that's this part, right? That's this part of the Turing machine. It just runs W. It just runs M on W. And if M halts on W, then accept. Okay. So this is rewritten a version. This is rewritten the general procedure of the Turing machine N. Okay. And so this is good enough for the assignments and the final. And then 2 would just be arguing what I was saying before. So 2 would be arguing this if and only if, right? So if the answer to the instance of the halting problem is yes, that means that M halts on X, right? So if M halts on X, then this line, right, this if condition is going to evaluate to true. And so then the Turing machine N is going to accept the input string. Right? So N will accept X. Otherwise, if M halts on X, halts, I just wrote the same thing. Come on. Loops on X. If M loops on X, then, well, what's the correct thing to write here? Should I write N rejects X? No, right? Good. Very good. Because rejecting would mean halting. So that doesn't happen. What actually happens is N, if I could erase this, is N loops on X. But if it loops on X, it doesn't accept. Okay? And so now at this point, I have all the ingredients for my mapping reduction. The only thing I really need to check is whether the instance modifier was computable. Well, if I look at the instance modifier, I'm not doing anything illegal, right? I'm just saying, take the, so if you're talking about the instance modifier in terms of strings, take the description, the string description of M, and then just add an extra small description which says if you get to either the original accept or reject state, then go to some new accept state. So sounds computable to me, and we'll show that a bit more formally after. But the instance modification is computable. And so therefore we have that the halting problem mapping reduces to the acceptance problem. And since the halting problem is undecidable, then so is the acceptance problem. Why? Because otherwise, if the acceptance problem was decidable, then we could use the acceptance problem solver to solve the halting problem. Okay. And so this shows undecidability for the acceptance problem. Okay, good. Any questions about this? No? Good. Right. Sienna. Well, I did, right? I did. Yeah, it's just, yeah. I could have also shown, you could have done it. So Sienna's question is, did we not skip over the if and only if? Well, in the second line, I'm just doing the contrapositive. Right? So it's fine. Any other questions? Oh, and yes. Yeah. Well, it's computable because the only thing you're doing is you're sticking an accept state to the accept and reject state, right? So I think a good question, though, is what would be an uncomputable instance modifier, right? So an uncomputable instance modifier, and this is what Prakash was talking about, is if in this algorithm, and so I think I should talk about this now, actually. So this is an extremely common error. Please don't do this in the final. I'm sure some of you will, but please don't. Okay. So what would make this uncomputable is if I added an else. Right? So if I say, if M halts on W, then accept, else, I don't know, the loop. This looks like it's computable, right? The reason why we think it looks like it's computable is, well, you know, I've just written it here. It's an algorithm. I just wrote down the steps. It's clearly computable, right? But no, it isn't, right? It isn't, because you have to think back to your Turing machine, right? If you think back to your Turing machine, how are you actually going to check this else condition, right? You need some kind of gizmo that checks that you're looping in the Turing machine, right? But if you could do that, then the halting problem would be decidable, right? But it's not, right? So if you could do this, right, if you could do this, then there would be a contradiction already in your instance modifier, right? And so you would get, well, I would get sad. Okay? So that's why it's not computable, because this else, right, this else actually has to be implemented in a Turing machine. But if you could implement this else in a Turing machine, that means that there would be some computable way to check that a machine is looping. But if you could do that, then you could decide the halting problem. But we know that we can't do that from choosing. Right? Yeah? For it to be decidable, there has to be no loops. Is that the question? Right, but yeah, so I think, yeah, so in a Turing complete formalism, and in a Turing complete formalism, there's always a chance of loops. So really the more general question is, in a Turing complete formalism, is there a chance for this to be uncomputable? And the answer is yes. Yeah. Yes? Aha. Right, so the reason why, so the question was, why is it in this argument here, no. In this argument here, right, that we can just talk about the halting of M, right? So good question. So the reason why is because remember what I'm actually doing is I'm saying if I have a yes instance of the halting problem, then I have a yes instance of the acceptance problem. But a yes instance of the halting problem is M halts on X, right? That's what it means for the answer to an instance of the halting problem to be yes. Right? So if it's no, then that means that M does not halt on X, meaning that it loops. Right? Yeah, that's right. Yeah, exactly. Yeah, exactly. Yeah. Any other questions? No? Good. Great. Excellent. So hopefully this is clear. I'm very happy if it's clear. If it's not, please ask me more questions. Okay, so what I'd like to do now is, now that I've given you a first example of a mapping reduction, I'd like to formalize this notion. So what are we actually doing? So let me give you the formal definition of the mapping reduction. So suppose I have, and to do that, like I said, I'm going to revert back to formal language theory notation. So now I'm going to talk about the languages corresponding to problems, but really there's a one-to-one correspondence, right? But for things to be slightly more formal, I'll talk about them in terms of languages. So suppose I have two non-empty alphabets, and I have two languages. So these could be the languages corresponding to decision problems, L1 and L2. Right, so L1 is defined over sigma, L2 is defined over gamma. It could be that sigma is equal to gamma, right? Or it could be that it isn't. And so we say that a mapping reduction, which is also sometimes called a many-to-one, but I won't use that term here. Reduction of L1 to L2 is a total computable function f from sigma star to gamma star, where the following is true. For every x in sigma star, x is in L1, if and only if f of x is in L2. Okay, so notice here that I've said total computable. I could have just said computable. I really want to emphasize the fact that the function is total, and total just means that it's completely defined for all of sigma star. That's what total means. Okay, and then I have that this reduction function f has this additional property here. So if we have such a function, so if such a function exists, then we say that L1 mapping reduces to L2. Okay, so at this point you might be thinking, how does this relate back to, you know, our example? This seems much more abstract than what we were dealing with. Well, actually, this is exactly what we were talking about. Okay, and so to illustrate this, I'm going to use a picture. So suppose I have this blob, which represents sigma star. And suppose I have this other blob, which represents gamma star. Again, sigma and gamma could be the same. I'm just saying that, you know, maybe they're different. That's equally as likely. Okay. And so in sigma star, I have my language L1. So L1 is just a subset of sigma star. And so you can think of it as partitioning sigma star. Right? So I have L1 here, and I have L1 complement here. And then L2 does the same thing for gamma star. So maybe here, L2 partitions gamma star. So remember, the intuition here is that L1 and L2 are really representing the languages corresponding to the decision problems. So if I have some string x in here, right, x is in L1, by the definition of what it means for a language to correspond to a decision problem, then this x, really, so x is a yes instance to the decision problem of L1. Right? That's what x, for x to be in L1, that's what it means in terms of its decision problem. Now, instead, if I have some string y in L1 complement, then two things can happen, actually. So the first thing is that y is just some arbitrary string that actually isn't a valid encoding of my problem, right? So y just doesn't correspond because, you know, this is the set of all possible strings, right? So if you're talking about the halting problem and the strings which encode instances of the halting problem, there are strings which don't encode instances of the halting problem, right? So, you know, maybe 0, 1 probably doesn't encode an instance of the halting problem because you need a good amount of letters to encode at least one instance. So either y is an invalid encoding, or it's a valid encoding, but it's a no answer, right? So y is a valid encoding, but the answer is no. Okay? And so what f is doing with this restriction is it's saying if I have some string in L1, so if I have some, oh no, okay, my laptop just died, but everything's okay. Okay, so if I have some string in L1, then that means that I have a yes instance, and what f is doing is it's mapping this yes instance to the set L2. So f of x2 is here, f of x is here. So really what this is saying is that f preserves the answer to the instance of the problem, right? So in this case, x goes from L1 to L2. Well, f of x here is a yes instance to the L2 decision problem. Okay. Whereas because of this condition, if y is not in L1, then it must map outside of L2, right? So it must map to somewhere outside of L2. So a no instance of the decision problem L1 maps to a no instance of the decision problem corresponding to L2. Okay? So in other words, F preserves the answer to L1, right? And this is extremely important, right? Because if I want to show reduction, if I want to show that solving L2 is enough for solving L1, and I have this mapping reduction F, then this is exactly what I need. Because I could just say, take an instance of L1, map it with F to an instance of L2, solve it using my solver for L2, and then map it back, right? Map the answer back. And so I can exactly do this because of what F has in terms of its properties. Okay? Yeah? Yeah? Yeah, exactly. Yeah, exactly. Yeah. So invalid encoding is also just not an instance. Yeah, exactly. Any other questions? Okay, good. All right. So now I'd like to give you an example of a function f, and really it's just going to be an example formalizing the instance modifier of the acceptance of the halting problem reduces to the acceptance problem. So in this example here, so in example A, the total computable function was f, which actually went from 0, 1 star to 0, 1 star, because instances of the halting problem and the acceptance problem can both be encoded just in binary, so it's good enough for us. And so what f is in this case is, f takes some input string, let's say v, and if v is a valid instance of the halting problem, so if v looks like the encoding mx, then what f of v returns is an encoding nx, right? Where n is as described, so as described in example A. If instead it's not, right? If it's not a valid instance, so if it's not a valid instance, so I guess I should just write otherwise, then, just map it to some invalid instance of the halting problem. So one possible invalid instance could be, the empty string. Probably not a valid instance of any problem. Right? Or maybe any interesting problem, I'll say. Okay? Okay. And so f is clearly computable. F is computable. So I don't have to write total computable, really. Because consider the Turing machine F. Consider the Turing machine F, which computes it. So what f does is on input v, it first checks if v is some valid encoding of the halting problem. So you don't even really need a Turing machine to do that. You could just use like a regex, right? Okay. And then the other thing is if the answer is no, well, the job is very easy. Just return the empty string. So return the empty string. Otherwise, if the answer is yes, then return the encoding, the string encoding of nx, where n was defined, as, on input and yada yada, yada yada yada, right? Okay. And so this showed that I did actually have a formal mapping reduction from the language corresponding to the halting problem to the language corresponding to the acceptance problem. Okay? So I've just formalized what I've done in example A. That's all I'm doing. Okay. So now what I'd like to do is I'd like to formally state the theorem that tells me that if I do have a mapping reduction, then I can show undecidability. So to do that, I'll state the following theorem. So suppose I have two non-empty alphabets again. I have a language over sigma and a language over gamma. And in addition, I have that L1 mapping reduces to L2. And L2 is decidable. Then this theorem tells me that L1 is also decidable. Decidable. So for the undecidability, that's just going to be the contrapositive, right? So this is the theorem. Now I'd like to prove it, because the proof is quite elegant and doesn't take that much time. So the proof is, well, suppose, right? Suppose L2 is decidable. If L2 is decidable, then what does that mean? By definition, it means that there is some Turing machine M2 such that the language accepted by M2 is L2, and M2 halts on every input. Okay? That's by assumption, right? And then since I also have a mapping reduction, from L1 to L2, then there exists a mapping reduction function, f, which is total computable, i.e. there is a Turing machine f which computes f, well, capital F, which computes lowercase f. Okay, so this is, all I've done really is I've stated the hypothesis, right? And so now, to show that this theorem is true, I need to show that I can create a Turing machine M1 which decides L1. Right? That's what it will have meant for L1 to be decidable. Okay. So, well, how do I do that? Let's construct a Turing machine M1 which decides L1 as follows. So M1 on input X will do the following. So the first thing it will do is it will simulate F on X to compute f of X. Well, what if f loops forever? Yeah. Right. F is supposed to be computable, so that's not a problem. Thank you, Louis. Good. Thanks. Okay. So that's not a problem. I can do this. I can simulate f on x to compute f of x. So at some point, eventually, in a finite number of steps, I'll get f of x. So then at that point, I'll simulate M2 on f of x. So I'll simulate M2 on f of x. If M2 accepts, then M1 accepts. Otherwise reject. Okay. What about this step? In this step, is this otherwise okay? Louis? M2 is also a Turing machine which halts on every input, so yes, it's okay. Right? Okay, good, thanks. Okay, and so this is my Turing machine M1, which I'm claiming decides L1. So the first claim is that M1 halts on every input. Well, of course, this is true because F halts on every input and M2 halts on every input, so I have a Turing machine which halts on every input. Now, the other thing I need to show is that the language accepted by M1 is equal to the language L sub 1. Right? And so this isn't all that bad either. because suppose that x is in the language accepted by M1. Well, this is true if and only if this line executes, right, by construction of M1. So if this line executes, then that means that M2 will have accepted f of x. So that means that M2 accepts f of x. So if that's true, you know, in other words, i.e. f of x is in L of M2. But because I, in my hypothesis, know that the language accepted by M2 is L2, then f of x is in L2. And so now how can I get from f of x, how can I argue that f of x in L2 if and only if x in L1? Yeah? Because it's not quite that. Because it's a mapping reduction. And so in a mapping reduction, I have this condition. Right? And so then, of course, I have that x is in L1. So f is a mapping reduction. I was looking at you like that because I wanted you to say just that. Looking for that single word. Okay, good. And so that proves the theorem. And so the contrapositive, right, so this theorem said that if L1 mapping reduces to L2 and L2 is decidable, then L1 must also be decidable. And this makes sense, right? If you just look at the direction of the reduction, right? This is saying that L2 is at least as hard as L1. So L2 is enough for solving L1. Well, if I can solve L2, then I should be able to solve L1. That's what this statement is saying. So it's just formalizing the intuitive notion that I've been given, right? And so then the contrapositive is just if L1 is undecidable, then so must L2. So the contrapositive is just, so the contrapositive is if L1 mapping reduces to L2 and L1 is undecidable, then so is L2. Okay. Good. Any questions about the proof or the theorem? No? Okay. All right. So let's see. Let me leave this as an exercise just to make sure that people have understood this notion of mapping reduction. So this is a true-false question. And it states that if L1 mapping reduces to L2, then L1 complement mapping reduces to L2 complement. So if you know the answer, don't shout it out. I'll leave this as an exercise. Okay. So what I'd like to do now is I'd like to give you another example of a mapping reduction. So here I have this formal argument that the HP to AP reduction was correct. I think I'll skip it because it's not that interesting, but I'll post it later. So I had another exercise here which would just show the correctness of L HP mapping reduces to L of AP. So I'll just post this later. Because with the time I have left, I'd like to look at another mapping reduction. This one is just a bit trickier. So I'm going to do another mapping reduction where I'm going to show that another decision problem is undecidable. And in this case, I want to show that the all problem is undecidable by showing that the acceptance problem mapping reduces to the all problem. Okay. So now you're probably wondering, what is the all problem? So the all problem is given certain Turing machine M. The all problem asks, given a Turing machine M, is L of m equal to sigma star. Right? So now it's not asking whether the Turing machine accepts a single string, it's asking whether the Turing machine accepts all strings. Right? So to me, that does sound like a harder problem, because now not only do I need to check this for one instance, I need to check this for every instance. So sounds a bit harder. Yeah. Okay. So how am I going to do this? Well, the general strategy, like I said before, is the first thing to do. Given some instance of the acceptance problem, I want to convert it to a particular instance of the all problem. Right? So what's an instance of the acceptance problem? It's a string encoding of m and x. Right? So it's asking, does m accept x? And what's an instance of the all problem? Well, it's just some Turing machine. Right? It's some Turing machine n, right, which is encoded using strings over the alphabet 0, 1. And we're asking, does the language accepted by n equal sigma star? So I need to convert an instance of the acceptance problem to an instance of the all problem as a function of that initial acceptance problem instance. Okay. So remember the second thing I need to argue that the answer to I sub AP is yes, and only if the answer to I sub A all is yes. Okay. So again, to actually do the instance modification, I'm going to use step 2 as a hint. Right? So if the answer to I sub AP is yes, that means that m should accept x. Right? And if the answer to I sub all is yes, that means that n should accept every string. Right? Well, there's a hint there. The hint is that, well, I could maybe just run m on x, and I check if m accepts x. If it does, then n should accept every x. Should accept every string. Right? And that's exactly what I'll do. Right? So that's exactly what I'll do. So for 1, the Turing machine n on some input w, So n is a Turing machine. Turing machines take input strings. And you can't assume that as your input you got x, right? So what you can do is you can say, well, I don't really care what my input string is. What I actually want to do is I want to run m on x. Right? So to do that, let's just erase w from the tape. Okay, clearly a computable step. You can erase things. Okay. Then the second thing you'll do is you'll load x. You'll load x onto the tape. So how do you have access to x? Well, I'm making the Turing machine n as a function of mmx, right? So I know a priori what mmx are. So in other words, you can think of mmx hard-coded into the control unit of n. Right? So, if you ask how, well, x is hard-coded in n's control unit. Okay? So you load x onto the tape, and then you simulate m on x. So you simulate m on x. Again, how do you know what m is? Well, you've also hard-coded m into your control unit. So you simulate m on x, right? And so m is running, it's running, and then maybe at some point it accepts x. And so if it does, if m accepts x, then the Turing machine n will accept. And the Turing machine n will accept. Okay. And this is the instance modification. So now let's actually check that it works. So if the instance to the acceptance problem, the answer was yes, then that would mean that m accepts x, right? So if m accepts x, then that means that after some finite number of time, this if condition would evaluate to true, and then the Turing machine n would accept. Right? But it would accept regardless of what w was. Right? So regardless of what the input string w was, n will accept. Meaning that n is going to accept for any string. Right? So if n accepts for any string, well, what is L of n? L of n is just sigma star. Right? Otherwise, if m does not accept x, so either it rejects x or it loops forever, right? Then this condition never executes. This if condition is never true. And so you never get to the then. But this is the only way that the Turing machine n accepts. Right? So if it can never get to here, that means that on any input string w, n is never going to get to an accept state. Well, that just means that n rejects everything. Well, no. Shouldn't have said that. N doesn't accept any input string. Right? So that means that n does not accept, so I shouldn't have said rejected, my bad, does not accept any input string. Well, if n does not accept any input string, well, by definition, that means that L of n is empty. And so now let's check that the answer being yes to the acceptance problem is also yes for the all problem. Well, if the answer is yes here, then the answer is also yes here. And if the answer is no here, then the answer is also no here, because L of n is the empty set, which is clearly not sigma star. And so we've shown that solving all is sufficient for solving AP. So we have that AP mapping reduces to all. But since AP is undecidable, so is the all problem. Okay? So we'll do many more examples on Tuesday, and we'll continue our discussion of undecidability then. Thanks very much. Have a nice weekend. So I really hope this recorded. Hmm.